Alright, my name is Dr. Marion Carroll again. This is organic what is this? This is general chemistry over at South Central Louisiana Technical College in Reserve, Louisiana. And I'm on lecture 6, I believe. Here we're going to transition into bonds, forming bonds, ionic and covalent bonds. We'll talk a little bit about the periodic table and the periodic variations associated in that table. So before I go into that, we finished our previous discussion about percent composition. One practical example I wanted to give you is that determining percent composition is important in determining what your molecular formula is. If you weren't clear on that, you can get an empirical formula. Simply based on the composition of the sample that you have. Alright, and there are various means of identifying both qualitative and quantitative what you have in a sample. So let's say, for instance, I have 300 grams of some element, or it could be a mixture of elements, I don't know for sure, that I had analyzed. And it was found to have 192 grams of oxygen, 56.7 grams of nitrogen, and 48.6 grams of magnesium. Alright, and again, we can do this by mass spec, ICP, HPLC, a number of different sophisticated analytical techniques that will tell you how much and in what ratio these elements are. Again, what is the first thing we want to do when we talk about elements is we want to determine their ratio, actually their molar concentration. We can do that. But let's say we weren't familiar with, we didn't have our periodic table, and so we weren't sure. So what we want to do is determine its composition in this total. Again, part over whole times 100. Alright, so we have 192 grams, which is the part over the whole gram, times 100 will give us 64%. And this is of our oxygen. Our nitrogen, we have, what did I have? 56.7 grams over 100 grams. And that will give us 18.9%. And our magnesium, we found 48.6 grams in that 300 gram sample. And so here we have 16.2%. Alright, so once we've done these calculations, someone discovered what the atomic mass units for each of these elements are. We know oxygen is 15.99 atomic mass units or grams per mole. Nitrogen is 14.00, and what is it for magnesium? 24.2. I think it's try to keep these in 2 places after the decimal. Okay, magnesium is 24.3 O and or O1, and nitrogen is 14.00, oxygen 15.99. Alright, so if we divided our gram molecular weight into the percentage, then we would get close to what would be considered our ratio, molar ratio. If we divided 64 by 15, sorry, you'll get 4.0. 18.9 by 14, you'll get 1.35, and 16.2 by 24 will give you 0.67. So with this as our molar ratio, we need whole numbers. We divide it by the smallest number, 67, 0.67, to get our whole number ratio, which will be 1 to 2 to 6. So we have 6 moles of oxygen, 2 moles of nitrogen, and 1 of magnesium. So we can actually create a empirical formula which consists of O6 and 2 M1, Mg1. And when we talk about our nomenclature, which will be coming up soon, we actually know that this ratio of elements can be reduced. Alright, our positive cations always go first in the formula, followed by our non-metal anions, and in this case nitrogen and oxygen are bound covalently, and the whole compound now is magnesium nitrate. We have 6 oxygens, 2 nitrogens, and 1 magnesium. Alright, that was a little refresher. So let's move on to bonding and give us a little introduction here. Bonding of elements requires the interaction of their free available electrons. Okay, and so where do you find the free electrons? Okay, free electrons are referred to as the valence electrons, and they're usually found in the outer shell. Alright, if you remember, the shells go from 1 to 7. Subshells are what? S, P, D, and F. And orbitals, okay, there are 2 in S, there are 3, there's 1 in S, 3 in P, 5 in D, and 7 orbitals in F. And of course the electrons that occupy those orbitals are 2 for S, 6 for P, 10 for D, and 14 for F. So let's look at the configuration of, let's say, lithium. Lithium is 1s2, 2s1. There are only 3 electrons in lithium, and the valence electron is the electron in the outer shell. So lithium has 1 valence electron. We can also represent the spin of those electrons by using the arrow notation. When an orbital is full, electrons spin in opposite directions. 2 in the s, but in the s orbital on the second shell there's only 1. And we indicate that with a single arrow. Let's look at chloride. Instead of writing out the whole configuration, we're going to write the last or the outer shell. 3s2, 3p5. So we have 3s with a full shell, and we have 3p, and it's not quite full, so each orbital has to fill first. Remember, we have 3 orbitals in p, and we can contain 6 electrons, but in this case we only have 5, so only the first 2 orbitals of the 3 are filled, and we're left with 1 electron in the third orbital. And so how many valence electrons are present in chloride? This is the third shell. 6 here, or 2, 4, 5 here, and 2 here. That's 7. We have 7 valence electrons in chloride. One thing to note is that lithium is in group 1A with 1 valence electron. Okay, I didn't note that up here. It has 3 total, but only 1 valence in shell 2. Okay, chloride, it has 7 valence electrons, and note it's in group 7A. So you see a pattern. The group number in the periodic table is equivalent to the number of valence electrons in the outer shell of those elements. Alright, so we're going to be, we'll move on into part 2 with a discussion of these bonding and how we use what's called the Lewis dot structure to represent the valence electrons. Let's quickly look at an example. If I have the configuration of sulfur, sulfur is in what? Group 4A. So what does that mean? That means that there are 4 valence electrons in the outer shell of, is it sulfur? I think it's silicon. Which one did I have? Silicon or sulfur? I think I had silicon yet. This is Si. Alright. Silicon is in group 4, and it has 4 valence electrons. What's the configuration, electron configuration? We'll do the whole thing. 1s2, 2s2, 2p6, 3s2, and 3p2. How many electrons? 10 and 4 is 14 electrons total. And the outer shell, what is the outer shell? Okay, the shells, again, are 1 through 7. 1, 2, 3. The outer shell is 3. And the number of electrons in the outer shell is 4. Okay, and so if we were to draw the Lewis dot structure for silicon, we would have to put 1, 2, 3, 4 electrons represented as dots around each side of that element. Alright, we'll look at some more of these examples in part 2.